Right, so without further ado, here's the new version of the array notation. You have here a namespace, and it has two members, a title, a presenter. The title is a character matrix, and the presenter is a vector of text vectors. So the way we show a namespace is by having parentheses, which normally cannot contain a line break or multiple statements. So by having it over multiple lines, it's a new syntax. We have colons here to declare the names, and then we have arrays inside. We're using square brackets with multiple statements inside. That becomes a matrix. It can be extended to higher rank. And because it's a flat matrix, it means things get padded to appropriate lengths. So as if you were to mix these three lines together. And a vector of text vectors. Here we use an extension to the strand notation, which uses round parentheses over multiple statements. Each statement becomes an element in this vector. And you can, of course, as you've always been able to, switch between line breaks and using diamonds. So this allows you to inline the notation. And in fact, you can adjust white spaces whichever way you want. So if you go back to the matrix, you can move in the square bracket, and you could also arrange things over as many lines as you want. And that's pretty much it. Thank you so much. But if you want some more details, I have more slides. Don't worry, it's less than 100. Let's look at the normal arrays and not references, not namespaces first. So we have here a matrix and a vector of text vectors. But first, what do I mean by this being version 3 of it? So for me, it started in Sicily when Phil Last presented his array notation proposal for such. And that went into FlipDB that he was working on as part of something called Acre. And that was a notation for extended rank. So you could have matrices higher rank than that. And that survived onto Acre version 4, which became its own standalone thing, not part of FlipDB. And this, again, only for high rank. I was inspired by this. I made an internal, in Dyalog, proposal for something that just extended strand notation to have deeper nesting of vectors. But what I actually presented a year ago was similar to what Phil has come up with, just extending rank. And then finally now, managed to come up with something that extends both rank and depth, so you can write pretty much anything. And meanwhile, I didn't know about this, but Phil Last had also been working on his notation. And so his notation also extends both to deep depth and high rank. In fact, our notations for normal arrays came out identical. Look at that. So maybe we can all merge. There's one little difference with regards to namespaces, but it looks like we're moving in a singular direction. First, a little bit about the background. What is it, again, we want to do here? Obviously, we can write scalars in APL. We can write vectors. We can write vectors of vectors with parentheses in strand notation. But more than that, it becomes really complicated, or you just can't do it. And it's strange because we have this array language that doesn't have a representation for arrays. So what motivated us to come up with a notation for this? APL has been around for half a century, and we didn't have a notation for it. Well, if you look at people's code, then they come up with array, notation, kind of. You'll see interesting things like this. I'm sure you've written this. So this constructs a matrix piece by piece, but it's not a notation, and it doesn't give you a good view of the array. It just constructs this notation little by little. So it's a matrix, and it contains some nested vectors inside. You can find interesting constructs like this, where what we actually want is just one long vector of text vectors, but spread over multiple lines. So these variables that are being used in the process of creating the array are never used again. Then you find even more exotic things like this. This is just a vector of two-element vectors, but there's a lot of noise going on with all these defins. We'll get back to how it actually works. And one of the most extreme ones, again, this is just a table, but it drowns in additional syntax that's not actually doing anything. In order to be able to see what we're doing, I'll turn boxing on. So we have scalars, we have vectors of vectors. We don't have more complex nested arrays and higher rank, and here are some examples of how that could look in the notation. Normally, if you write a vector, you would write something like this. And if it takes up too much space, you're in trouble. You'll have very long lines in your code. But this notation allows you to break things over multiple lines. So every statement inside these parentheses that span multiple lines becomes an element in itself. And of course, you can use diamonds instead. So you can inline this, serialize data, and you can spread things to the width that is comfortable for you by mixing diamonds and new lines. Matrices, we don't have a notation for, but it works exactly the same way. Every statement becomes one row of your matrix. You can use diamonds instead. And here's an example of what it could look like. So here you have what you would normally write, or an example of what you could write, and what it would look like with this notation. In my opinion, a really clean way of writing it. Here's a character matrix. And again, you don't have to worry about getting the number of spaces right. If, in the traditional way of writing it, we have here on the left, you don't get the number of trailing spaces right, you'd get the length error. And text vector of vectors works exactly the same way. Of course, white space is important here. Here's a Boolean matrix. It shows you in another way that people sometimes do this with transpose and table to make things right, so you can start extending your matrix. But let's say you wanted to have a vector of matrices. So the way it's currently done is by using some temporary variable that you build up from the bottom, and then you concatenate things together, and then eventually have to clean up after yourself. And with this new notation, you would be able to write it in what I think at least is a very intuitive manner. You can see in the parentheses, this is a vector, and then you can see inside that it has a bunch of matrices of different sizes. You don't have to declare anything with the size it has. You can do higher rank, and that gets even worse with the current way of writing things. You can't even see anything anymore. You'd have to just imagine it based on the shape that you give in. But you can very much see the structure of your high rank array with the notation. And in fact, if you ignore the square brackets, that's actually how APL would normally print a high rank array. And you can also see the similarity between these square brackets and the boxed output of an array. So here's a more complex nested example of it. We have an error table like we have in Conga. And we can have vectors of vectors, which are currently awkward to put together over multiple lines of code. But it becomes really simple with this notation. And of course, you can adjust it. You can use more width. And you can inline everything using diamonds instead of new lines. So this is how it works. If you have round parentheses with multiple statements inside, then every element in the final array is constructed from one statement in this multi-statement notation. And we go from inside and out. So this is just a recursive definition of it. And that's really all there is to it. Take a statement, it becomes an element from inside and out. If you have square brackets, then it works in very much the same way from the beginning. We begin with statements. These become major cells in the array. And we go from inside and out. There's just a couple of more things. In order for this to actually extend the rank, let's say you had a scalar as a major cell, then it would just become a vector, which is not necessary because we already have a vector notation. So instead, every deepest level element has to be at least a vector. So we just enforce that. We treat it as a vector even if it looks like a scalar. And then we mix everything together, of course, because arrays have to be orthogonal, rectangular. So we pad those out with appropriate data types, just like you would always do if you mix. Some more examples for your enjoyment. A matrix of some data. And you can spread things out over multiple lines. This one also shows you how you could write a one-element vector without using APL primitives. Of course, you're free to use any APL expression you want inside this notation, but if you don't want to use primitives, if you want to have it just a constant, then you have a way of writing that by saying to APL, this parenthesis goes over multiple statements, so it's a vector, and the first element of the vector is 301 in this case. Here's some real-life examples. So we saw this one before. This builds up a matrix. It's how it looks right now if you look in the code that comes with Dyalog. And if we line things up, which you could do if you're using text files, then you don't have to worry about auto-formatting, removing your blanks, then you can see the structure much better of what's going on. And then we can remodel that into using the array notation. Now, I personally don't like parentheses very much. If there are too many of them inside each other, I get really confused on which layer am I at. So we can use diamonds instead, and then you can see the structure easier. That's as personal style. You can do it whichever way you want. Here's an example from defense, calendar, and again, we're doing a bottom-up declaration of our array, generating these 4 variables that we don't actually need. We are removing blanks just so that things can line up. And then there are some comments for parts of it for each quarter of the year. So let's remove the blanks, keeping things in text files, and then switching to array notation, and we can still comment the lines. So you can have comments inside the notation for an array and tell the reader what the different parts of your array signify. And so again, this is a single vector of text vectors, and we use a mixture of diamonds and new lines to get it to an appropriate width that's nice to read and can be commented in a meaningful way. This example that I showed before, which is just a table, a vector of vectors actually. And it might look like it's pretty obvious. You have these text vectors on the right and you have some values on, but then you notice that there is a reversal going on up here. And the reason for that is because we begin on the very right with a tilde, so that's the very bottom right. And then we take that and we concatenate on the right another element, and that becomes the argument to the next to last function, which takes that and concatenates one more thing on the right. So the author here wanted the reading order from top to bottom to correspond to the actual array that you get out in the end, but the way APL executes made it in opposite order, so it threw in a reverse there, so you can to fool you into thinking that what you see is what you get. So space this out so we can see what's going on, and remove all that noise, and this is the array you get. In fact, you can see it begins with a mix because it's actually transposing kind of this vector of vectors, so we could change that into just giving it a proper matrix because that's what you're using. Or, of course, we could flip everything on its side. This example, pay attention because there will be a quiz on this one. So here, again, you might think it's the same thing as the previous one. We begin from the end and we just concatenate more pieces. This time it's concatenated on the right instead of on the left, so then we don't need a reversal. But then you notice this guy. So hands up anybody who, at a glance, can just tell me what that does. Oh, really? Right. Do you believe me if I tell you that it removes spaces from the second element of every sub-element of this vector of vectors? Kind of, except for the last element, though. Right, exactly. So in the array notation, you could just write this as a long vector of 2-element vectors, and you can split it up whichever way you want. And now, because you paid attention, of course, and we got rid of all this noise, you'll notice the typo, right? You see this dash was not supposed to be there. Because if you look at the left parenthesis, the right parenthesis, they're the same. We fixed this in version 17, though. So, the array notation, the part of it that's just about simple arrays, it is really something that's kind of glaringly missing from APL, because other languages that do have some kind of arrays, even though they're simpler, more primitive than APLs are, they have notations for it. So JavaScript has, okay, it's the parent of JSON at least, the JSON notation, which allows you to write explicitly how the whole array looks. And when I teach APL and I tell people about how arrays work and how you manipulate them and so on, I get stuck really quickly because I need to teach them row and enclose and comma before they can even begin to understand how the arrays work. Because I can't show them what an array looks like. And people ask me, so how do I write a matrix? Well, you can't. It's also useful because it's a fairly simple, straightforward notation. And it means we could teach a listener how this notation works. Even though they have no concept of APL, they could have a concept about this notation. And so other systems that have both rank and depth, so things like NumPy and MATLAB, and J, of course, they could learn this notation, and you could communicate back and forth using this notation. Of course, you can, because it's a text form of any array, you'd be able to edit it in any way you want. You could write tacit functions that include arrays as part of the formula. You could just write that array as it is instead of having to construct it at the definition time. And of course, we always go about storing your source files as text, and all the benefits that comes of that. So I said, well, JavaScript has JSON. Why don't we just use JSON? So the reason we can't just use JSON is because JSON has no concept of rank. That means that JSON can't distinguish between a one-by-one matrix and a vector of a vector. So there's a lot of loss of information like this. It doesn't have the concept of a character. It only has the concept of a string. And so that means you can't just round trip to JSON and back. And notation clashes with APL. So for example, this one at the bottom, quote ABC quote, and square brackets 1, 2. What is that? So if it's just normal APL, it's indexing into ABC. But you could also say that the first element is an APL vector and the second element is a JSON vector. That would mean something else. Or you could even go as far as to say that you have the square bracket is a JSON vector, and inside it has an APL expression. So the APL expression's value is to the first element of it's a whole mess. You can't do it. Okay, it's not going to work. So we can't use JSON for anything except for communicating with the world outside, of course. And for that and all IT-related things, JSON is very good. There are some special cases with regards to upping the rank, and it just works out nicely in many cases. So you can write a column matrix. It looks like a column matrix, and what you get is a column matrix because we enforce that every statement is at least a vector, at least rank 1. And you can even do trailing X's that are empty just by having tildes or quotes at the very end, and it just works out. Same thing goes for depth. You can write a single vector over multiple lines, and that just works. It becomes a vector as a vector. And you can write in any way. You can use APL expressions inside. You can even write one-element vectors with this notation. There still are some things that we can't do with the notation. We can't write an enclose over enclose of something. We could come up with a different character or set of characters to show that this is further enclosed, but then we might as well just use the enclosed character. So there are different ways you could write your things. And then I just made this change this morning because I spoke with Zach Batik about this notation, and he said, well, maybe there's a way we can deal with empty arrays, because the display function or high-level boxing can show you something by showing some elements and then saying, but they're not actually there, it's just a prototype. And so if you, just like you can write enclose in front of an array to make an enclose, then you could also write 0/bar in front of an array. And that would collapse the first dimension. So this would show us that we don't actually want all the elements here. We just want this to declare the prototype. So we could come up with a character for it, but I don't know if it's even necessary. Some things are a bit awkward. If you make, say, a matrix of matrices, you might think you could just write it the way APL would normally print it out to the session, just add in the square brackets everywhere. You can't do that, because if you look really carefully, what happens here is we start reading on the top left, and we see square bracket, 2, 7, square bracket, which means we're going to read it like this, right? And then that means we have 5 elements in the first statement on this inner array, and things are going to go really bad from there. So what you have to do instead is you write it like this. If you tilt your head, it looks okay. But you can also just inline the inner arrays, and then it looks okay as well. So in summary, you can write with this notation arrays, multiple lines, or inline, rank, and depth. Now onto the namespace aspect of the notation. So here we can see we have a parenthesis over multiple members, and then declaration, member name, colon, and its value. We also don't have such a notation. We can only create namespaces in various roundabout ways. One of the easiest ways that I use to create a simple namespace is I write it in JSON, and then I use quad.json to convert it to APL. And that's, of course, is very sad. So again, we want to have a way to write an APL namespace fully populated without having to first teach the poor students quad.ns and quad.fix and quad.json. And again, this is a very simple, straightforward notation, and we could teach others to use this with all the same benefits. And also, something you can use these inline namespaces for, and here you can see some examples of them, is to supply named arguments to functions. So that's something when you have a lot of different parameters to your function, then things kind of start drowning in the order of arguments. I'm sure you've seen this before. And you have to supply lots of zilders and quotes and other things as placeholders to show that I only want to modify from the default, the umpteenth argument. But instead, in other languages, you can name arguments when you call a function and say, I want this argument with this name to be such and such. So then you could have a function that takes a namespace as argument, and it dots into that namespace and picks out the pieces that it needs and supplies defaults for the other ones. And you could just call the function with an inline namespace notation right next to it. That's really convenient. We could also potentially let you do this with variant, because variant really just takes a namespace, but it's written in a quote, name of parameter form, quote, and then the actual value. But really what it's trying to do is set up an options namespace. So you could have a nice notation for that. We could also imagine extending things like quad R, so that we have a convention. Normally you can replace a bunch of different strings with a bunch of other strings, or you could run a function on all the matches, but you don't have a way to specify one function per match string. But we could have some kind of convention for doing so if we supply a namespace with multiple functions inline. And finally, this would also at least mostly solve the problem you sometimes have that you want to temporarily change the state of the APL machine to use quad.io0 or similar things. And so this would allow you to create a tiny little namespace and then use the iota or the division or the equality or whatever inside that little namespace. It has like its own version of the APL primitive with that different environment, just for that moment where you're using it, and then you continue. So currently you can't create a namespace literally. You only have to build it up piece by piece, and instead you would be able to just write name and value. And you can see the similarity here between JSON and APL. And you can write inline also. Of course, it works the same way as we does with all the arrays. You can use diamonds instead of using new lines. Actually, if you look at the top, it doesn't really return the same result as the bottom ones, because the result of an assignment is a pass-through value, is whatever's on the right of the assignment. So that will give you 42 APL. So really, you have to write this in order to get the actual namespace back. That's really awkward. So I'll go a little bit more in depth on that in a moment. You can also use functions inside the namespace. The only way to do that currently is by copying them in piece by piece and then getting rid of them afterwards. It's not very easy. Or you can assign into it if they're defs or derived functions. But in this notation, you could just write them literally inside the run parenthesis. You could also do a mixture of scripted and unscripted namespaces. So you could have members that are inside that are just declared with :class, :namespace, and so on. And you could create a script. So currently you have to create a script and then fix that and get rid of the source you created. But you can already, with the notation, because we have the vector notation, you could have a vector of text vectors and then use quad fix on that. So you can directly inline create a scripted namespace like this, but have it look nicely over multiple lines instead of a single long line. And we could also allow you to put :class inside the notation. So here's an example. Don't have time to dwell on it too much, but you can see a lot of different things you can put inside a namespace. Literally everything. Here is what you would do if you want to build up a library of binary matrices with names. So currently you have to repeat all these declarations over and over and over again. It gets a lot of noise. Whereas with a notation, you're able to just write literally what it is you want. Finally, an empty namespace, JSON notation, which uses curly braces, just clamps them all together. There's nothing inside. That's an empty namespace. Since we're using round parentheses, we can do the same thing. It doesn't have meaning currently, and this is something that occurs very much in code, generating a namespace and doing something with it. I'm going to very quickly go through this because there isn't enough time. There's a little bit of question here. What do you do with the scope? What happens if you use the same name over and over again? So what is r.a? Because we've both declared an a and assigned to an a and used the a from outside. So it is as if every member of the namespace is created in its own container based on the environment outside. And so the C here, which uses a, gets the a from outside. It is as if you were to put in a defin that has its own little scope and run that in the environment outside. So it works the same way. And you can compare this, which seems funny, compare this to if you wrote :namespace in the script, and then wrote this surrounding defins to get the scope right. It would give you the same result. Tangentially related to this, but once we get this right, we should really have this as well. I showed you the expression to generate a namespace with certain names and values. So let's say we have names, we have values, you want to put them together. You can create this helper function, and in fact, we have a lot of code that does things like this, but it's really hard to get it right on the first try. So wouldn't it be nice if you could just write this? Right? Create a namespace. Normally, quad NS can take a list of names to populate your namespace with, but if you could also give it a deeper nested argument, and you could give it names and values, and you could do the opposite. You can extract all the names and values out of a namespace. I have a model for this, and you can go online, you can play around with it. I can't guarantee that the model that, especially the one that generates the notation based on an existing array, always gets it right. I think there's some special cases where it gets it wrong, and there are some limitations to it, but you feel free to play with it. And the one that I evaluated, I think, is a little bit more stable. Here's a summary of how it works in the namespaces. So we have literal namespaces. We can have an empty namespace, populate a namespace. And this is my summary slide. Thank you.